So in this problem, we have a 8,600 kilogram match car that is traveling at 16 meters a second, and it slams head on to a car B of mass unknown, okay, and it's at rest. After the collision, both cars are moving at 6.5 meters a second, and they're moving together, okay? So this tells us that this is a perfectly inelastic collision. So what does that mean? Well, that means that we can couple the masses at the end of this problem, and we'll get to that. I'll show what that means. So we know to solve these sort of problems, we need that the momentum initial equals the momentum final, right? It's that conservation of momentum idea that you've learned about. Okay, what are the initial momentums and what are the final momentums, right? Well, let's see here. So we have car A traveling at 16 meters a second. We know that momentum equals mass times velocity, right? It's just a velocity with a factor of mass in it, right? So we have that 8,600 kilograms. Oh, geez, I won't get to that far yet. Let's actually define our variables. I'm getting ahead of myself. So the mass of A times the velocity of A initial, right? So this is the initial momentum of this car. I'm going to add that to the mass of B, right? And its velocity initial of B initial is equal to the mass of A velocity final plus mass of B velocity final. Now you could keep it like this, right? Notice how I didn't give the final velocity a subscript of which car we're talking about, right? When they stick together, they're moving at the same velocity. That means that these terms here are equal to each other, right? And what does that mean? If I have, for example, 3x squared plus x, right? What can I take out of here that's the same? Well, they both have an x, so I could take out x, 3x plus 1, right? It's the same kind of idea with what I'm about to do, right? Of factoring something out that's the same or like terms that they both share. I can just factor out the velocity, right? So the velocity final is a times of the mass of A plus the mass of B, okay? Hopefully that makes sense there. So the mass of A, velocity of A initial plus mass of B, velocity of B initial is equal to that final velocity. So this equation perfectly represents it. We have that initial velocity here of 16 meters a second. This one is going to reflect that it's at rest. And then this final velocity is they're sticking together. They're like one body, right? If I'm 141 pounds, if I gain 60 more pounds, that's part of me, right? That moves with me. That's the same concept here. This mass plus this mass is now one system moving in the same velocity, right? Hopefully that makes sense of what I'm saying, relatively so. So we have that equation here. Now let's begin to solve. So we know the mass of A is 1,600 kilograms. And by the way, I don't know if I said this, you're asked to solve for the mass. Hope that was somewhat obvious. And if you're watching this video, you're probably looking for an answer. So sorry about that. So that mass times its velocity of 16 meters a second, right? What is, so that's this term here. What's this one gonna be? Well, the mass is submass, but the velocity initial is zero. So what happens to this term, right? If it's some mass B times 0 meters a second, well, that just cancels out. It's not part of our equation anymore. So we can just get rid of that. And in fact, I'll just get rid of the term here. So now we're left with the final velocity, which is 6.5 meters a second times the mass of A plus the mass of B. We don't know the mass of B. That's what we're trying to find here, right? The mass of B is the unknown. So what can we do? Well, notice how this is a multiplied term by something in parentheses. It's a term multiplied by a term, I don't know, binomial, right? So I don't know why that was so hard for me. Let's multiply this out first. And when you multiply a kilogram by velocity, you get a Newton second. So 1.376 times 10 to the 1, 2, 3, 4, 5. You get a Newton second. Why is it a Newton second? Well, notice kilograms, a Newton is equal to a kilogram meter per second. Okay, a Newton per second, geez. Kilogram meter per second a second. A Newton second is a kilogram meter second to the 1. So notice there's a difference of exponents. If you multiply a Newton by a second, right? So it's really kilogram meter per second squared. If I multiply it by a second, one of the seconds cancels out, and we're left with a Newton second. So hopefully that idea makes sense of why our units are in Newton seconds, right? You could obviously put it as kilograms by a multiplied factor of velocity. That's also fine. But moving on, we're gonna multiply this out to each term respectively, right? Remember from algebra, if you have 3x plus y, you could enter that in and get 3x plus 3y. You distribute a term to the other terms there. Makes sense? That's what we're doing with our velocity. So 6.5 times our mass of A gives us 55900 Newton seconds plus 6.5 meters a second mass of B, right? And these are multiplied terms. Okay, so hopefully that part makes sense. Now let's subtract this over. So 1.67 times 10 to the 5th Newton seconds minus 55,900 Newton seconds. So we actually get, when we subtract that over, is 81,100 Newton seconds equals 6.5 meters a second mass of B. I'm going to expand this side a little bit, and we're going to actually write out the Newton second, a kilogram per meter per second. Okay. If I divide both sides by the 6.5 meters a second, we'll notice what happens to our units, right? If we divide by a meter, it's going to cancel meters. It's going to be meter over meter, cancels. And if we divide by a reciprocal second, remember, if we divide by something, that exponent swaps and it becomes a second on the top of our fraction, and that's going to cancel out our seconds. So let's go ahead and do that, and it will just leave us with kilograms, and that will be the mass of our car. So we do the math, we get it to be 12,476 kilograms is equal to the mass of B. That's our solution. That's the mass of the car. Hope you guys enjoyed.